Picture this. You're sitting at a coffee shop, checking your watch. You're waiting for a friend, and she's running late. Naturally, you need to figure out why she isn't here yet. You don't have all the facts, right? So what does your brain do? It immediately starts trying to fill in the blanks. Your mind rapidly spins up a few possibilities. 1, she's actually on time and your watch is just fast. 2, she got stuck in traffic. Or 3, she was abducted by aliens. Now, logic instantly rolls out that first one because, well, she's visibly not sitting across from you. But what about the other 2? Your human intuition automatically assigns a really high plausibility to traffic and a very, very low plausibility to alien abduction. You aren't doing rigid true or false math in your head here. You're naturally weighing plausibilities based on your knowledge of how the world actually works. And you know what? That intuitive ability to weigh plausibilities instead of just relying on strict black and white facts is exactly what artificial intelligence needs to make sense of our noisy, unpredictable world. In this explainer, we're focusing on exactly that, why AI needs probabilistic reasoning. We're going to explore how giving machines the ability to handle uncertainty transforms them from rigid calculators into truly intelligent, adaptable decision makers.
Okay, section 1, beyond true and false, the limits of Boolean logic.
To really understand how a modern AI thinks, we first have to look at where classical programming totally hits a wall when faced with uncertainty. On one side, we've got traditional Boolean logic. It operates on strict true or false values. Now, that's fantastic for basic math and clear-cut rules. But it is terrible when data is missing, unclear, or noisy, which, let's face it, is almost always the case in the real world. On the flip side, we have probabilistic reasoning. Based on the Cox-Janes model of plausible reasoning, this approach gives an AI continuous degrees of plausibility. Instead of just a 0 or a 1, it generalizes logic for the real world. It basically allows a machine to say, hey, I'm not 100% sure, but this seems highly likely based on the evidence.
Moving to section 2, the mathematics of uncertainty, quantifying the unknown. We all know humans do this intuitively, but how do we translate that human common sense into actual math that a machine can process? Well, we use probability. By quantifying uncertainty into a probability, like say calculating a 60% chance of rain, AI systems avoid getting paralyzed by incomplete information. Instead of just crashing or throwing an error because a single fact is missing, the AI assigns a mathematical probability and just keeps on functioning. And this is a brilliant shift in computing. Instead of a flat, rigid landscape of simple yes or no decisions, the AI is now navigating a complex, continuous 3D distribution of probabilities to find the most likely truth. It's treating variables continuously, evaluating these peaks and valleys of likelihood. That mathematical structure allows an AI to map out all the possible outcomes and basically hike its way to the highest peak of plausibility. Which brings us to section 3. Updating beliefs with Bayes, the core engine of AI.
But here's the thing, an AI isn't just a static snapshot. Our world is constantly changing, meaning an AI has to constantly adapt as new information rolls in. And it does this using Bayes' theorem in 3 really vital steps. First, it holds what's called a prior probability. That's its current belief about a situation. Second, it observes new evidence. So if it's predicting the weather, it might note that, oh, dark clouds are suddenly appearing. Third, it updates that initial belief to a new posterior probability. The chance of rain might jump from 30% to 80%, based entirely on that new observation. There's a fantastic quote that really hits the nail on the head here. It says, Bayes' theorem allows us to invert the relationship between parameters and the data. Therefore, Bayes' theorem is sometimes called the probabilistic inverse. This probabilistic inverse is literally the mathematical magic that allows an AI to constantly refine its predictions and actually learn from past experiences. It's not just guessing data based on rigid parameters anymore. It's using real-world data to continually redefine the parameters of its own understanding.
Let's dive into section 4, modeling an unpredictable world, frameworks of uncertainty.
So now that we have the math, the probabilities, and Bayes' theorem, how does an AI architect actually map out this uncertainty to build a functioning system? Well, one foundational tool is the Markov model. These models predict the future state of a system based only on the present state, completely ignoring the past. This is known as the memoryless property. And it's so important because it simplifies incredibly complex environments by assuming the next step only depends on exactly where the AI is right now.
If an AI had to calculate the entire history of everything before making a single move, it would just freeze up.
Now, standard Markov models are great, but they do require all states to be directly observable. And in the real world, things are hidden from us. So when an AI can't see the whole picture, the system upgrades to hidden Markov models, or HMMs. These extend the standard models to infer hidden or unobservable conditions using the statistical likelihoods of the data it actually can observe. Basically, it guesses what's hidden based on what's visible. And AI architects don't stop there. They combine these techniques into massive networks and decision processes to navigate environments, take actions, and get rewards. We've got Bayesian networks, which use graphs where nodes are variables and edges show conditional probabilities. Then you have probabilistic graphical models, which scale that up for incredibly complex systems. And Markov decision processes, or MDPs, model an agent's interaction with an environment to maximize expected rewards. That right there is the absolute cornerstone of reinforcement learning. Finally, Section 5, Real-World Impact and Challenges, Weighing the Trade-offs. So, where does this mathematical framework actually show up in our daily lives? Honestly, the applications are genuinely everywhere. In robotics, it powers SLAM, simultaneous localization and mapping, allowing a robot to navigate your living room or explore completely unknown terrain. In healthcare, probabilistic models use symptoms and test results to predict disease likelihood. For natural language processing, it handles the incredible ambiguity of human speech for translation and voice recognition. And in finance, it's used for predicting market trends and modeling risks. From your smart speaker to medical AI, probabilistic reasoning is the engine handling the messiness of the real world. It is, however, a massive balancing act. While probabilistic AI brings tremendous advantages, like flexibility, robustness against noisy data, and super effective decision support, it comes with some pretty steep challenges. The high complexity means these models are computationally very expensive. They need massive processing power. They are also incredibly reliant on data quality. If you feed the system noisy, incomplete, or biased data, its probabilities are going to be wildly inaccurate. And finally, interpretability is tough. Explaining exactly how a massive probability model reached a specific decision is often really difficult for non-experts to grasp.
But despite those heavy computational costs and challenges, one truth remains. Continuous adjustment helps AI stay accurate. Allowing an AI to continuously adjust its probabilities as new data rolls in is currently the only reliable way to achieve functional intelligence in a dynamic world. It is literally how AI survives when the rules of the game constantly shift.
I want to leave you with this final, somewhat provocative thought. If an AI builds its entire worldview on the probability of what has already happened, how do we prepare it for a future it has never seen? Think about it. If something truly unprecedented happens, an event with a past probability of absolute zero, how will the AI react? Thank you so much for exploring the math and logic of AI with me today in this explainer. I hope you're walking away with a much clearer understanding of exactly how machines learn to navigate our incredibly uncertain world.